So guys, we were talking about complex numbers yesterday. So we defined doing serving the set C of complex numbers. C is of elements of the form x plus iy, where x, y are in R, and I is just a symbol, so that I squared is minus 1. Addition on this set is defined in the following way. How do I define this? So just x plus x prime plus I, y plus y prime. Again, this is the I is just a symbol, okay? Whenever you have I squared, what do you put it? Minus 1. Yeah? A bit bigger, okay. Okay, how do you define the product? So it's x prime minus y prime. What as well? I x, what? I y prime x plus y x prime. Okay. Now, I will post more notes on complex numbers. We will revisit them. But the idea is that to see that C is a field. Definitely, I will prove that this is a field. I will post notes on that. So C is a field. Now, if you just want to take the inverse of some element, and x plus iy is 0, if and only if x is equal to 0 and y is equal to 0. I will show you how to prove that. I mean, these are things that are kind of obvious when you look at them, right? But so I will, and then if you want to take the inverse of an element, so if xy is different than 0, 0, how do you do that? So take x plus y times x minus iy over x squared plus y squared. What do you get? A squared minus b squared, right? B squared, it becomes ix squared, so you get x squared plus y squared on top, divided by x squared plus y squared, which is 1. And then, if you want to take the inverse of something, what you do is you want to cancel the I. So you just multiply 1 minus 5i on top and bottom. So 1 plus 25 over 26. Okay? This is how we take the inverse of a complex number, non-zero complex number. Okay, so is it clear? Is this clear? Yeah. Okay, so I'll post more notes on this. We will see more complex numbers. We will definitely see more complex numbers, but now I prefer to do something else. More about rings. Okay, any questions on that?
Is that 1 minus I side divided by 2?
1 minus 5 side. What's 1 plus 5i times 1 minus 5i? This is 26, right? Should I expand this? Should I expand this or that's okay? It's okay, right? 1 minus 5i plus 5i plus 25. Yeah? Okay, great. Okay, now I want to talk about the product ring. Definition. Let R in S be rings. Then R cross S is a ring with operation take an element Rs plus, R prime S prime, how do you define this addition? You just add them in their respective rings, right? The addition in R, the addition in S. And how do you multiply them? Everyone, how do you multiply them? How could you multiply it?
Multiply the R's together.
Multiply the R's together. R and multiply the S's together. What is the identity for addition in this ring? What do you think the identity for addition in this ring is?
Identity of R, identity of S.
Exactly, so what is it? So it's 0R, 0S, right? So 0R, 0S identity, or neutral element for plus. And what is the identity element for multiplication? Yeah? 1R, 1S. Neutral element for times. Now, is R cross S an integral domain? Can R cross S be an integral domain or not? Pay attention. R cross S is not an integral domain. It's not a domain. Of course, under these operations, right? Under these operations. Why is that? Let me take 1R, 0S, times 0R, 1S. Are these 0 elements of the quotient of the product? Are these 0? Is 1R 0? Is it this neutral element for addition or not?
No.
Is this element neutral for addition or not? No. Is this element neutral for addition or not? Yes or no?
No.
Yeah.
Like there shouldn't be like S times S.
Thank you. Thank you. Thank you. Thanks. Is this 0 or not? Everybody, is this 0 or not? No. Is this 0 or not? Is it 0?
No.
Does it look 0? Is it the neutral element for addition? Say no.
No.
No, exactly. This is 0R, 0S. So those two are 0 divisors if the rings are commutative. Okay? It's not an integral domain. Okay, even if R and S are commutative, you take the product of these two elements, you get 0, 0. And these are non-zero elements. Okay, so please pay attention. Great. Now let's move on to ideals. Ideals. So ideals will just restrict to commutative rings. We will not talk about ideals and non-commutative rings. Okay? So in the discussion, if I omit the condition that R is commutative, then please remind me. Or, I'll always assume it's commutative whenever I talk about ideals. Okay? So let R be a commutative ring. A non-empty subset I of R is called an ideal if 1 I plus is a subgroup of R plus. Of course, the plus, I could go away without putting it, but let's put it. And the second important property of ideals, if R belongs to R and A belongs to I, implies RA belongs to I. Okay? So basically it's a subgroup. And it's closed under taking products in R. So if you have an element in I, and you take an element in R, then their product will lie in I. Okay? Now, where does commutative play come into role here? Come into play. Where does the role of commutativity come into play? Where do you guys think? Yes. In? Yeah, but what part? You mean here? RA, exactly. So commutative, RA is equal to AR. So it doesn't matter where you multiply the R.
No.
Now, if it's non-commutative, you have a notion of left-sided ideal, and right-sided ideal. And you have a notion of two-sided ideals, if the ring R is not commutative. But we'll not worry about that. We'll just worry about commutative rings. Okay? Great. Is the definition clear? Okay, so let's talk about ideals of Z then. Z is a ring. Ideals of Z. Play. Let I be an ideal of Z. Then I is equal to nz for some n in n union 0. Proof? Let me change this. Let me do it a stronger word. Well, no, let's keep it. Okay, let's do it. Nz, is an ideal of Z for any n in n union 0. And 2, if I is an ideal of Z, then I is equal to nz for some n in n
Union 0.
union 0. Okay, let's prove that. Great, let's prove that.
Sorry, what's in the first line?
For
I see
any
N.
n in n union 0. Yeah.
What is... Wait, you mean n union 0, that means like all the integers including 0? The positive?
Yeah, all the positive integers including 0. Yeah. Okay? Great. So, let me write this down. Proof. So let n be in n union 0. Then we know that nz is a subgroup of Z, right? I mean, if n is equal to 0, nz is just 0. And if n is equal to 1, nz is just Z. Right? We see that? Remember this? Do we? nz is a subgroup of Z, right? And let R be an nz, then, let R be in Z, and A be an nz. What can I say about A? Then A is equal to nq for some q in Z, and Rk would be equal to R nq, which is n second claim that if I is an ideal, then I is equal to nz for some
So,
n union 0. Yeah.
so why do we look only at n equals 0 and
No,
n equals
just as an
1
example,
for
because these
those
are
just examples?
yeah. I mean, if these are the trivial ones, right?
But for all other ones,
Yeah,
how does
it works. The proof works, right? nz is a subgroup of z.
yeah,
For
but
any
like z is infinite, no?
yeah, but nz is a subgroup of z, right? For any n. No? 2z is a subgroup of z. 3z is a subgroup of z. 4z is a subgroup of z. 5z is a subgroup of z. 0z is a subgroup of z.
Because those are the sets of multiples of n.
Exactly. And these are precisely the ideals. Exactly. And they're closed under multiplication by r, right? R is in z and a in nz, so RA will belong to nz. Yeah? Oh, great. Now 2 is easier. Let I be an ideal. And z. And I is a subgroup of z. We know, what do we know about the subgroup of z? They are of the form nz for some n, right? We know this about the subgroups of z.
We never saw that, but
You saw this in homework where you proved that every the subgroup of a cyclic group is cyclic.
yes, but z is wait.
Yeah?
Okay, z is
You remember that? It's the subgroup of a cyclic group is cyclic, and you pick the smallest element n that belongs to the ideal of this to the subgroup. You remember that, right? Or no? You remember this or no? Okay, so
no.
then I is a subgroup of z, hence I is equal to nz for some n union 0, C homework 5, and X session 1. Okay? I prove this. So, okay? Great. Quotient rings. Oh no, let me do something first. I want to do something first. Okay? Let R be a commutative ring. This is an important theorem, very important theorem. R is a field if and only if the only ideals of R are 0 and onwards. Of course, you can check that the 0 is an ideal, right? Is 0 a subgroup of R or not? Is 0 a subgroup of R or not? Say yes or no? Yes. Now, R times 0, is it equal to 0? So 0 is an ideal. Now take the whole ring R. Is it a subgroup of itself? Yeah. And if you take any element R times an element in R, you get back an element in R. Right?
Yes.
So 0 and R are ideals of R. Maybe let's prove it. 0R is always, note, 0R is always an ideal of R, and R is always an ideal of R. Now, let's prove this way. Which way you want to start? This way or this way? This way. So if R is a field, then the ideals are 0 and 1. Which one do you prefer? This way? Okay, let's do this way. So suppose R is a field. And let I be a non-zero ideal of R. What do I want to show here? I want to show that I is equal to, very good, I is equal to R. Very good. Now if R is a field and I is a non-zero ideal, what can I say about I? What does it mean to be non-zero ideal? Contains a non-zero element, right? Then there exists A and R, A different than 0 R, such that A belongs to I. Isn't that right? This is what it means to be non-zero. Okay, now R is a field. What can I use? What do I know about fields?
You can inverse.
I can find an inverse. Very good. I'm very
To get the identity element.
let B be in R be such that AB is equal to 1 R. This is since R is a field. R is a field and A is non-zero. AB is equal to B, of course, because R is commutative. Can I claim that the identity belongs to my ideal or not?
Yes.
Look at the second property of the ideal. If I have an element in my ideal, and I hit it by, I multiply it by an element in R, I still land in the ideal. Right? Do you see that? Everybody, do you see that? Look at the second property of ideals. If R belongs to R and A belongs to I, then RA belongs to I. B is in R, A is in I. This implies that BA belongs to I. Isn't that right? Can you have a look? Is that clear?
Yeah.
What is BA?
1 or
1. R belongs to I. Great. Now let R be an R. What can I say about R1R? 1 belongs to I, and R belongs to R. Agree so far? So what can I say about R? It's in? It's in R. Very good. So any R in R, oops, it's in I. Sorry. What did I say? So any R in R is in I. If any R in R is in I, then R is a subset of I. We know that I is a subset of R. So R is I. Are we good here? Yes? Is it clear? Okay. Let's look at the second one. Oops, I don't want to erase this. Okay, now the second one will be a bit, I did it, but we'll do it again. I mean, we will give a more formal definition, but I want to do it from scratch here. Now suppose that the only ideals of R are 0, R, and R is commutative. What do I need to show? I need to show that R is a field. Great. What does it mean that R is a field? That I take a non-zero element and I can find for it an multiplicative inverse, right? Now how do I do that with ideals? So I give you a non-zero element A. Let's talk about groups. I give you a non-identity element A. Can you find a subgroup that is generated by A? What do?
You take its order or something?
You take its powers, right? A, yes. A squared, A cubed, A inverse, A minus 2, right? Yeah?
Yeah.
Here we'll do the same thing. Let A be an R, be non-zero. Now, how can I construct a subgroup? Well, a subgroup of R that is an ideal that contains A.
Multiply A with itself until you get the identity element.
Well, but A is not necessarily invertible here. R is a field, not a group. Right? R is a ring, not a group. Right?
Not necessarily a field yet.
It's not a field yet. Yeah, but it's not necessarily a field. For now. Now let's think a bit about it. Take A and consider the set of all multiples of A. Multiply, consider the set. I take A and multiply it by all elements in R. Is that an ideal or not?
Yes.
Check. I is an ideal. That's very important. Okay? And I is an ideal of R. Why is that? Everybody, why is that? Does 0 belong in I? Is I a subgroup? Does 0 belong in I?
Yes,
Why?
because R is all the elements in R,
Yeah,
and so 0 times A is
exactly. That's very good. Oh, okay, it's recording. 0R belongs to I. And 0R is equal to 0R times A. Agree? Everybody? Now, if I have two elements in I, does the sum of the two of them belong to I or not? See heads nodding, but I want someone to help me.
The what?
Does x plus y belong? What? Yes.
Yeah, because you can distribute and then it just.
Exactly. So if x belongs to I, what can I write x as? Then x is equal to some, I don't know, let's R1 times A. And y is equal to R2 times A for some R1, R2, and R. Now what is x plus y? It's R1A plus R2A.
Yes.
What can I do now? Yep.
Some belong together.
Rewrite it as A multiplied by R1 plus R2.
Very good. Thank you very much. Or A times R1 plus R2. Doesn't matter. Because R is commutative. Okay? So x plus y belongs to I. Great. What do I need more for a subgroup? I need that, the additive inverse. Does minus x belong to I or not?
Yes.
Everyone? Anyone can help me why?
Yes.
Yep.
You could make the inverse by making some x equal to the inverse of r.
Exactly. Minus x plus I. Very good, thank you. Since minus x is just equal to minus r, 1 times a. Is that clear? Everybody, any questions? So I is a subgroup of R plus. Great. I need it to be an ideal. So I need the second condition to be met. Is the second condition met? So if you take R times X for any R in R, do you still land in I or not?
Yes.
Any help?
Yes.
Someone help?
Yes.
Someone else? R times X, do you still land in R or not?
It's a middle.
Yeah? Why?
Well, because we can do the same thing if we write x is r1 times a, and y is r2 times a.
No. Oh, no, I'm saying X is, R is in R, so what, maybe I should write it down. So if R is in R, but you have the right idea that if R is in R, does Rx belong to I?
Yes.
How can you write Rx as? R, R1, A. And then R1 belongs to R. Thank you. Which hence XR1 RX1 belongs to I. So I is an ideal. We'll call this and we'll have this. We will call this ideal a particular name, but I is an ideal. Now, is I a zero ideal or not? Is I 0? Yes.
Does it say if r exists in r?
Yeah, if R is in R. X1, oh no, I wrote X, then Rx belongs to I. Agree or not? Everybody? Is it clear? Yes?
Yes.
Okay. So I is an ideal of R. Is I the zero ideal or not? By assumption, is I the zero ideal or not?
No, but it contains a.
Exactly. I is different than 0, R. Since A belongs to I. By assumption, what can I say about I? Look at the assumption. The only ideals are 0 and R. So if I is a non-zero ideal, what is I?
R.
I is equal to? Everybody? R. Then I is equal to R by assumption. Great. Now if I is equal to R by assumption, this means that 1 belongs, this implies that 1 belongs to I, hence 1 R. Agree? Now if 1 R belongs to I, this means that there exists R0 in I, R0 in R, such that R0 times A is equal to 1 R.
Why?
1 R belongs in I, right? Belongs to I. I is just the set of these elements. If 1 belongs here, then you can write it in this form. Are we clear? Are we good? I mean, R is commutative. R0 is equal to 1, since R is commutative. So R is it? Because since every non-zero element is invertible. Okay? I spent some time on this because it's important. This fact of taking all the R multiples of an element A will come into play later on. Okay, are we good with this? Is it clear? Any question? Yes? Non-zero element is invertible. Are we good? Any questions? Any questions? Please know this proof, yeah.
If 0R is an ideal of R, how do we know R is a field?
Oh, I'm saying that the only ideals of R are 0 and R. Okay, so I start by let I be a non-zero ideal, then I must be R. Okay? So I construct an ideal that is non-zero. Oh, you mean the other way? Which one you're talking?
No, like the way we're doing.
Oh, the way we're doing. So if I have this assumption, and you have a non-zero A, right? You can construct if you can manage to construct an ideal containing A, then this ideal is non-zero. Agree? Then what must it be?
It's
R, by assumption.
Yeah.
Okay?
But if it is 0.
If it is 0, then it doesn't count. It's only 0. Okay? A must be 0 for it to be 0. Okay? Of course, in all rings, I'm assuming that all rings have 1 different than 0. Okay? Great. Any more questions on that? Any more questions on this? Great. So now I'll introduce quotient rings. This is going to be a bit fast because basically you have seen the constructions. Quotient rings. Let R be a commutative ring. And I an ideal of R. Define the following relation. On R. We say that X is related to Y. I'll add a small I here. If only if X minus Y belongs to R, we write X is congruent to Y modulo the ideal I. Okay, just a notation. Okay? Basically, it's a generalization of modulo n. This means that X differs from Y by an element of I, right? This is what it means. If X minus Y belongs to I, why did I say if X minus Y belongs to R? No, of course, it's always true. Okay?
Makes more sense.
Yeah.
Does this simplify the following
Relation on R. We say that X is related to Y if and only if X minus Y belongs to I. Is an equivalence relation on R. Why is that? Since I is a subgroup of R. Right? We've seen this equivalence relation for subgroups, right? This is Y inverse X, so it's X minus, yeah. So R under multiplication is not a group. So, okay, R under multiplication is not a group. Not necessarily, it's not a group. If 0 is different than 1, it's not a group. Equivalence relation on R. Oh man, what's happening today? Thanks. I's and R's everywhere. Okay. Now, what are the equivalence classes of this equivalence relation? What do we know? The classes. The equivalence class of X and R is the coset X plus I. Right? This is the same relation we defined in Lagrange's theorem. You remember that? We remember this? Everybody? Do we remember this?
Yes.
If the operation is addition, what is y inverse x? It's minus y plus x, right? This is the same relation. Yeah? Do you remember this or no?
It's a weird one.
Yeah, we remember this? Everybody?
Can you repeat from the start what you wanted to ask? To
This is like, this is the this relation we have seen in subgroups.
the left process.
Y inverse x belongs to H. If the operation is addition, what does that become? Right? Yes?
That's the same equivalence that we use for the
Exactly, exactly. Yeah, yeah, yeah. Very good. Very good.
What did he say?
That's the. We remember this, no? Yes or no? I mean, yeah, we're using the full power of groups now. So the equivalence class of X and R is the coset X plus I. Okay? So what can I say about two cosets here? They're either equal or disjoint. And X plus I is equal to Y plus I if and only if what? Everyone, if and only if what? X minus Y, yeah, belongs to I. Someone said this. Someone said this? Yeah, someone said this there. The groups are going to follow us. They're going to follow us more now. Okay, so. Great.
Only if y minus x plus I minus y.
Denote by R mod I the set of left cosets of I. All of these notations have been seen so far, no?
Not in that way, but yes.
I mean, that's seen in subgroups, right? So, a set of left coset G mod H. R, I is a subgroup of R, so it's R mod I. Yeah? And R mod I is a ring. Yeah, now I'm going to use the full power of groups. So, like, and R mod I is a ring under the following operations. So how do I add two cosets? This should be obvious, right? This is in groups. We have seen this in groups. How do I add two cosets? How do you, yeah? Say, how do you add?
R1 plus R2 plus I.
Yeah, exactly.
Oh, really?
Very good. This is just the group operation. If H is a normal subgroup, XH times YH is equal to XYH.
Wait.
Yeah.
I is a normal subgroup of R?
Yes.
We haven't seen that, but
R is a billion, so every subgroup is normal. Right?
yes. Okay. I see.
R1 plus I. Now here is the R2 plus I. How do you define this? This is just R1, R2 plus I. Question?
What happened?
Okay, this is how you define the multiplication. Now what do we have to show when I define multiplication and operations on cosets?
Well defined?
We have to show it
Well defined.
well defined. Is the first one well defined?
But
or not?
Yes.
Is the first one well defined?
Yeah, because it's a normal subgroup.
The first one is a group operation on the quotient group.
Yes.
Right? Yeah, it's the operation of the quotient group, so it's well defined. Now what we have to show is that the second one is well defined. Okay, let's see if I have time. How much time do I have left? 4 minutes. I could do that. addition on R mod I is well defined, since I is a normal, well let's write I plus is a normal subgroup of R, right? Because R plus is a billion. Now what do you have to show? You have to show that multiplication is well defined. Well, suppose that R1 is congruent to R1 prime mod I. What does this congruence mean? Mean that the difference belongs to I. And R2 is congruent to R2 prime mod I. We need to show that R1, R2 minus R2, R2 prime belongs to I, or that R1, R2 is congruent to R1, R2 prime mod I. Let's do this. So what can I say? I can say that R1 is equal to R1 prime plus K, well, K is bad, plus, well, let's be K, for some K and I.
Wait, what? Sir?
And R2, yes sir.
Which R's have the prime or not?
Is it R1, R2 minus R1 prime? R2 prime?
So, no, I think that's good.
Yeah,
Oh,
but
the
there's
prime
only
zero,
one
yeah, the
prime.
prime zero, thank you, yeah.
Okay.
The primes are the second ones.
Okay.
So our two primes is R2 prime plus Q for some Q in I. What is R1, R2 minus R1 prime, R2 prime? Let's look at that. This is just R1 prime plus K times R2 prime plus Q minus R1 prime, R2 prime. Explain that. So again, I get R1, R2 minus R1 prime, R2 prime is equal to R1 prime, R2 prime. Everything is commutative, so plus K R2 prime plus Q R1 prime plus KQ minus R1 prime R2 prime. So what do we get? I get it's R2 prime times K plus R1 prime times Q plus QQ. Does this belong to I? K belongs to I, right?
Yes.
So R2 prime times K belongs to I. Because I is an ideal. Does Q belong to I? Yeah, so R1 prime times Q belongs to I. And here, it's an element in I times an element in R. It also belongs to I. Since I is a subgroup, this also belongs to I. Hence, R1, R2 plus I is equal to R1 prime, R2 prime plus I. Okay, let's call it a day. And then, so please review this stuff. You review groups. I mean, I'm going to assume